Thank you so much for that introduction. Thank you also for highlighting the interdisciplinary component of my background. And I want to start this talk by saying something that might be shocking or might just about hit the hit that sore spot that I think as a community we're really sort of starting to focus on, and that is that even things like the weather service can have a racial bias associated with it. And of course, that's not intentional. But for example, here there was a study looking at radar coverage. And data is really at the heart of the things that we do with machine learning. And if that data doesn't provide coverage in traditionally underserved areas, then that means that you have a racial bias. For example, if you're training your model to predict something like, say, a hurricane or flooding. So, really, what we want to do is to be able to harness these tools in a way that's sustainable and fair. And here I'm able to provide a little bit of insight on that today based on my own research in terms of how we can really pick the methods and combine them in the way that's consistent with our goals. And an outline here is that I'm first going to give a little bit of an introduction and talk about the scientific goals and challenges, look at data mining, and then also prediction, and very importantly, put all of this in the context of how can we make this trustworthy? How can we bust out of the black box? So jumping into the challenges here, to give this context, I also want to say that I am really excited about machine learning methodologies, and I think that the field of oceanography, for example, is really ready to take these methods and really create a lot of progress. And I've talked about this in a number of review articles. Some of them are cited there at the bottom. And I believe that we can do old things better and faster and more accurately, but also very importantly, really try to induce paradigm shifts that can really propel us forwards. And now, just so that we're all on the same page, I'll distinguish between unsupervised and supervised learning, although this really isn't a hard boundary, where for unsupervised learning, you can think of the top left there as the dots as data points. So for example, a point in latitude and longitude, and you have two dimensions there. So for example, temperature and pressure. And what you're trying to do, the machine learning model, is those green stippled lines on the top right, where we're trying to decide, okay, what belongs to where. And for supervised learning, the key difference is that you need some sort of labels. You need someone to have told you, okay, this is a blue dot and this is the red dot, so the bottom left. And the machine learning model here now is that green stippled line, this decision boundary, and this is what often is referred to as a black box. And what is really worth noting is that the two key developments that I think are important and that I'm targeting in my research is understanding why are predictions made and how uncertain are these predictions. And the uncertainty quantification is one that we don't talk about as much, but I think this is also really worth stressing. And what I'm excited about here is also really to explore, both for supervised and unsupervised methods, how can we gain new knowledge? And really, a lot of these things, a lot of the way that we think about this should be rooted in what we've already been doing for decades, and that is validation. And here on the top, you can see just an example from a sine curve of having data, the blue dots, and the true underlying model there in green, where the red line shows you that we've, on the left, underfit, and on the right, overfit. And really what we want is that sweet spot in the middle. And that is exactly the same in machine learning applications. So on the bottom, you can see just a classification example, but really a lot of these methodologies are ones that we know. We just need to port that knowledge, that way of thinking critically, to the machine learning framework. And just to highlight this again, really there's a trade-off between bias and variance that we need to be aware of, but might not necessarily be a bad thing for all of our applications. So high bias, for example, means that where your true model is that bullseye, you might consistently be hitting an area that's a little bit away, or if you have high variance but low bias, you're consistently sort of scattershot around that bullseye, that true model. And validation here is something that is an active area of research, one that I'm really interested in. where we can look at both internal methods of validation, so how cohesive are the different data points, are we separating them properly, but also external methods where we can bring in domain knowledge and really start to rethink how we're doing these things. And really, I think that this validation component and just understanding how it works and how we should think about it is just really exciting and really important. And in oceanography, and I think throughout the earth sciences, really, what we're having is this wonderful era of just having increasingly availability of good data. And here I'm just showing you a couple within oceanography, but you can really see that towards the modern day, really we have so much more data, and this is really great. We also have a lot more data from numerical models, and I'm just naming 2 data sources here. But this unprecedented amount of data and this high resolution data for numerical models, for example, really also creates a problem in the sense that, okay, we have this data, but how do we analyze it? How can we use methods to make this better and easier? And of course, the other thing that's very exciting about machine learning is how can we increase resolution even further, where a lot of machine learning methodologies are really coming in and potentially able to really move this forward. So it's becoming more apparent that if we just use brute force PDE solvers, this is going to be very difficult and will probably not happen in time. So how can we accelerate this? And of course, another really exciting thing that's been happening lately is that purely data-driven models, so purely machine learning models on their own, are being able to really quite skillfully do things like medium range weather forecasting. And there are a number of different groups doing this, but, and I really want to stress this, these are not necessarily really using domain experts. And of course, they're guided not necessarily by the principles that we think of as the most important. And of course, there are some domain experts involved here, but that is one of the areas that I want to highlight as potential areas where we could increase trust and increase adoption. So moving on to the data mining component here, and here I mean data mining that's using novel methods. So for example, if you think of, in terms of data mining, if you think of the Lego box there on the bottom left, you have a lot of exciting pieces and they're all jumbled together. They have lots of different components and classes like the shape and the color associated with them. And what we want to do in as a coherent and fair way as possible is sort them into different areas. And while that's a very basic example, that's what I want you to keep in mind here. And I wanted to highlight some of my own research here to give this context. And one thing that I've been able to pioneer is identifying regimes of ocean dynamics with theory-guided data science. So here I am taking oceanographic theory, clustering, and information theory to make a method that is able to do this fairly. And the thing that I did was take very complicated ocean model data and really boil this down to the dominant drivers and then ask, okay, are there patterns in these dominant drivers? And this is something that oceanographers have been doing basically since we've had access to coherent data. And here I'm showing you just one of those drivers to the left, and the patterns, the dynamical regions here denoted by the colors on the right. And we can see that, for example, in the pink areas, we have a balance that really is one of those canonical ones that we've been asking ourselves, okay, is this real, for a very long time? And here we can say yes, and it is in the areas that we expect, but we can also find entirely new things like that gray area on the bottom, where we can completely rethink, okay, how do we think about these structures of really important drivers within the circulation? And here there's the Southern Ocean around Antarctica that I'll be returning to in the end. And in terms of the new research that I'm doing here, just on the topic of validation and how do we make sure that this is actually fit for purpose for us, I want to highlight this work briefly, where we're taking and moving between different spaces. So a 3D embedding space and a 3D space of latitude, longitude, and depth here, and being able to validate using external methodologies that are much more intuitive for us as domain experts. And playing with this and trying to push the envelope and innovate in a direction that is domain specific and easy for us to use as a field is something that I think is very important and not discussed enough. So I now also want to spend some time, of course, with the prediction aspect. So for example, with neural networks, what you're trying to do very often is predict forwards in time and also tie all of this to what you can call trustworthy machine learning or trustworthy artificial intelligence, AI. And while this topic doesn't necessarily need an introduction, I think what we very often think about is this black box aspect. So this was in my title. And what we want to do is to make sure that if we open this black box, we don't find that actually spurious correlations in the data have led to predictions that might not be consistent. For example, if we move into a different realm, into a different climate scenario, where we're just looking at fundamentally different statistics in our data. And again, I want to stress, I am excited about these things. I'm highlighting a lot of bad things, but I think there's really huge scope for moving forwards. And methods exist, for example, that can peer into the black box. And some of these I'm going to highlight here. They're sometimes referred to as explainable AI or XAI, and they can be both model specific, so look into the machine learning model, or model agnostic, looking more at the data. And on the left there, you can see an image of a horse, where very often we use this example of, okay, can you recognize a horse, a cat, or a dog? And what you can do with these is, for example, look at, okay, what did the machine learning model actually look at? And this is one of those examples where you can see that what this model looked at to recognize a horse was the copyright sign on the bottom. Now, you might have a situation where every example that you have of a horse has a copyright sign at the bottom. No problem. But you might also be in the situation where a picture of a horse might not necessarily have that copyright sign. And for example, an analogy could be that if you're trying to predict something, and for example, all the data that you have recorded is recorded at different intervals, then maybe that's fine. Maybe all of your data will be consistent with this. And in that sense, returning to the bias and variance question, some of the problems that we're seeing might not necessarily always be ones that we should be focusing on. So taking a very critical view, but also being generous with the limitations that we have and how we collect data is really very important. And I also want to stress, and I'll return back to this, is that these methodologies are really a family of methods that are being actively developed within the machine learning community, and being part of that conversation and being part of this conversation between, okay, in what direction should we innovate, is something that I think is really important. Now, to an example. Here I'm showing you just a very simple linear model. And this linear model is one that can represent a lot of the emergent behavior in, for example, what we can think of as a mock Atlantic meridional overturning circulation. Here you have a low latitude box, so the tropics, and a high latitude box, say the subpolar North Atlantic. And you can think of this as being driven both by the temperature T and the salinity S in these boxes, together with a forcing, so here H, that if it's a freshwater example, like the one I'll be showing you, we're adding or taking away freshwater. And what we have is a circulation that can either be clockwise, temperature-driven, or counterclockwise, salinity-driven. And very interestingly, even this very simple linear model is able to exhibit abrupt shutdowns. So the question now is, can we verify that the machine learning has learned the true model behavior to capture this emergent behavior? And here I'm just showing you, okay, where do we get the data from? We get it from this model. It's called the Sonnewald model. And on the left there, you can see the forcing, H, here freshwater, and also the transport, or Q, which is an approximation of this overturning circulation. And you can see that we have these abrupt shutdowns. So you have the transport changing, and then suddenly, boom, all the way down to zero, and then moving up again. So really, this is a nice little toy model where we can then look at, okay, what did the machine learning emulator of this model actually do? And we can see that we do surprisingly well with this simple model. So the ground truth here, this Q, is in blue, while the prediction, so the machine learning model, is in orange. And we're able to capture those abrupt shutdowns. And the light blue is showing the uncertainty bars, which is also something that I mentioned is very important, and I'll return to. And what we can now do is to look into this model, which is linear, and say, okay, what do we actually look at? And there on the right, I'm showing you this, where the salinity was the most important feature, and the temperature, which I didn't mention, but is actually set to being slave to salinity, wasn't looked at all. And that inflection point happens exactly where we think it should be happening. So that gives me trust in terms of having the machine learning model actually having learned something about the Stommel model. And of course, that was a fairly simple example. So I also just want to highlight a more complicated example where we've actually been able to determine some new results in terms of the understanding of the circulation, where we were able to develop the method tracking global heating with ocean regimes, or THOR for short. And this is able to infer 3D subsurface circulation using only surface fields. And this is exciting for a number of reasons, because of course we're solving this very underdetermined and sparse problem of, okay, how do we go from the surface down to depth? And this is also something that's being actively used, for example, for looking at and understanding climate model variability. So on the right there is just a flow chart, and I also want to stress that in developing this, we specifically used methods that would be appropriate for using these explainability methods. So really, there's a lot in the design of this. And we use different explainable AI methodology that I also just want to quickly highlight. And here you can see two examples, or an example of a network being trained to recognize a cat. Here on the top, you can see the picture of the cat. And what you're doing with the networks is setting the weights and biases between these different nodes. And what you then have when you've trained this is that you can move backwards throughout the network and say, okay, if I add up these different contributions or relevances, what am I actually looking at? And on the back there, you can see, yes, the neural network is actually focused on the properties of a cat that I would say represent catness. And in that sense, of course, we're not interested in cats or dogs. We're interested in physics, in my case. And what we can then do is to really set up the problem so that I can use these XAI methodologies to validate that the model has actually conformed and reasoned like a scientist with GFD, and thus take a problem that is grounded in observations and grounded in the present day and use that more confidently in future scenarios where, of course, by default, we don't have data. We don't have data from the future. And here, in a sense as well, we're able to couple in uncertainty quantification. And here I'm showing you an example of my work where we're moving from having fixed weights and biases to using distributions. So again, just choosing our networks carefully. And here we're quantifying entropy to be able to say, okay, in areas where there's high certainty, the uncertainty, of course, is low, but areas where there's higher uncertainty are ones that really need a little bit more attention. And finally, I also just wanted to highlight this work that we're presenting at a NeurIPS workshop, one of the bigger machine learning conferences, where we've been able to reveal fundamental shifts in dynamics within climate change. So moving from having this current around Antarctica, the Antarctic circumpolar current, be moved from being bathymetrically locked, so really caring about the bathymetry, and moving from that not being as much of the case in a future scenario. We recombined THOR, the uncertainty quantification, and XAI to demonstrate this. And I'd be very happy, of course, to talk about that more. I just wanted to highlight this example. So to summarize here, I think what we really want to do is to go from tools to creating and communicating insight. And the things that I think are important here is to think about how do we demonstrate skill in a meaningful way? So how do we circumvent the skepticism that is still present in the community, where I hope I've demonstrated to you that I really see importance in validation, uncertainty quantification, and explainability. And for example, using machine learning to do weather predictions, maybe we're not really validating using the right fields. Maybe it would be more informative, and maybe it would be better in terms of creating trust to validate using different benchmarks and really having a conversation with the communities and the scientists that are potentially skeptical would be useful in terms of really increasing the value that we can get out. And what I also want to highlight here and 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 try to stress is that we need to distinguish between operational tools and tools for scientific discovery. Now, this boundary does not need to be hard, but I think there is just a fundamental shift between these two, where current methods are not always fit for purpose for either of those. So really thinking about that and constructing problems where machine learning methodologies are the best tools for the job is something that really we should think about. And I also want to stress that bringing domain experts into the design of, for example, models that we're using for forecasting or other methods that are, or other problems that are facing some resistance, are ways in which we can start building trust in the community. And I also want to stress here that it's important to realize that computer scientists and also industry really are performance focused, and that's not necessarily what's right for us as a community. And in terms of using these methods as well, it's worth stressing that these are methods that really are a field in and of themselves, and we need to build machine learning literacy. And in that sense, I also want to stress something that I've been seeing recently, because a lot of the peer review processes that we're using aren't necessarily good at reviewing the different ways in which these methods might not be used appropriately. So in that sense, we might be having a situation where important things are overlooked, which then of course can perpetuate misconceptions and thus perpetuate a lack of trust and a lack of using these methods in a consistent way in our community. But again, I want to stress that I think these methods are really exciting, and collaboration between fields is really key to success. And with that, I'm happy to take any questions you might have, and I'll exit full screen to be able to see you.
Okay, well, I have a question. I'll get things started. So I guess it's kind of ironic we're having this talk today, and you were talking about some of the stuff. I'm sure you probably heard about the GraphCast that came out from Google. And so, big, I can already hear those groans from several people on the panel, but that's fine. But yeah, so I mean, what you were mentioning, sort of this idea between performance and metrics of performance versus sort of, understanding the processes and doing that. So I know you're talking a lot about, for the ocean and maybe climate perspective, but I just wanted to maybe get your perspective maybe on, on the GraphCast, on the sort of these announcements now, right? Because it's not even just an announcement of, hey, we have this model, is, hey, we have this model and we have this paper in Science, right? So now it's kind of dual here, right? Where they're sort of trying to get a little credibility on sort of both sides, right? By having so just kind of thoughts on, I mean, is this the model we should see going forward, where we have a peer-reviewed article plus the actual metrics, and how do we go about that?
Well, I think it's worth noting how well these big models are doing. But of course, when you have those types of models, they're not necessarily ones that are that offer the type of information that, as a community where we're very used to physics-based models. So these, the models that we're used to thinking about, where we have actual physics, and the problem with these very big models that are used by and produced by these big companies is that they're not necessarily transparent, and it's not necessarily easy to go in and say, okay, has this feature been actually recognized for the right reasons?
Mhm.
They also, very importantly, aren't necessarily as good at resolving sharp features. So this is something that our traditional models can do. And like I tried to stress as well, I think the thing that they're trying to do, and of course, them wanting more credibility is something that I see as a good thing because it might enhance this conversation, which I think is really key. So I think it's important to stress that the way in which this might be perceived as competition might not necessarily be the best way of engaging with these more commercial entities. But of course, they're interested in performance, and that type of performance is not necessarily the type that we're after.
Hi, Mike. This is Bao. We are in the same building, but we haven't got a chance to have in-person communication. But it's very nice to see you virtually again. So it's thanks for a nice presentation. My question is about the model development. We know some kind of a bias, like for example, the MOM6 model. There's a equatorial. Some clients kind of too shallow. We have that kind of a code bias in the model.
Mm-hmm.
I'm just wondering whether there's some kind of effort to use a machine learning to target as a kind of a bias to understand what caused that bias and how to improve that kind of that bias in the model development effort. I'm not quite familiar with the Ocean Group doing, so
no,
just curious.
That's a very interesting question, and the Thor methodology that I highlighted is used and has potential for more use for just those types of questions. For example, there's a model in Los Alamos as well that's that has actually exactly that type of bias, where looking at the fundamental dynamics and how, for example, they might be parameterizing the interactions with bathymetry in a way that could be improved in certain areas is something that we're actively looking at and doing.
Very nice talk. I have to admit, I get a little tripped up sometimes by the lingo. Like we tend to refer to these climate and NWP models as physics-based, which I can understand. It's based on physical equations. But it feels like all of these AI methods are using them to some extent. Otherwise, they probably wouldn't be so successful. So I'm not. I don't even know if I have a question here. It's just more that, like, is that nomenclature correct? I mean, should we be calling the climate and NWP models physics based, and then the AI is something else? I'm just curious what your thoughts are on that.
Yeah, that's a great question. I think the key distinction there is that for the what I'm gonna call physics-based models, because it's just a useful distinction right now, is that they're grounded in the primitive equations for the ocean side. So the Navier-Stokes equations and the equation of state. So how heavy seawater is. So in that sense, you have grounded it in this set of equations that we know is useful. I'm going to use useful rather than correct here, because I think the definition of truth is kind of the heart of your question. You know, what is truth? What is physics? And in that sense, the physics-based models are ones where we have that grounding, but of course we have the problem of discretization. And that's really where you have that boundary between physics-based and machine learning-based that's I think, really interesting, because of that discretization, we have to parameterize. There just isn't a way of seeing everything. So for the atmosphere, for example, you have clouds. For the ocean, you have what's called eddies, and they do really important things, and we don't necessarily understand those. And we can't understand, we can't really parameterize or include in a way that we know respects the physical processes. And that's where saying taking a data-driven approach might be more sensible. So we don't have good equations to approximate those processes that we can't see. But I think calling the traditional models physics-based is still a more useful description of them. Where, for example, the machine learning-based models, they do take the data from those physics-based models and use that for their training. So in that sense, you could say that, hey, okay, they're maybe more able to encode both, the good things, but also the bad things of our models. And the thing that is also really interesting to me is that while in a machine learning model, you're getting a lot of, speed up, for example, but very importantly, you're also hard coding those errors. So, for example, if you have a physics-based models, we do a lot of development, and those mean that, okay, we take a parameter and we tweak it a little bit, and hey, it does a lot better. Which, of course, if you have a massive machine learning model, that retraining isn't necessarily very easy. So I think the interface between the two, where, for example, if you use a big coherent data set, so part of my group is trying to find a way of doing the sparse data inference where we have data in one area but not necessarily another, and sort of back out, okay, a more coherent observational field. And trying to kind of build on that interface between the physics-driven and the machine learning-driven to try and maybe fill in those gaps is something that's very interesting. And there are a lot of groups that are also trying to port and use machine learning to learn the very high resolution models to be able to put those, for example, into climate models. But like you were saying, the physics-based models aren't perfect. Like, we don't have scale separation. We have to discretize. And that final step might be the most important one. We just don't know.
Okay. First of all, great presentation. I learned a lot. My question is more actually not related to research, but probably more related to education, since you are also in the university. Now that we have a lot of companies, as you said, big companies investing in this in this industry, and how do you see that we should change our training of students, in terms of curriculum, in terms of how we do research for, PhD student research, like curriculum for undergraduates? Like, I'm just wondering what your thoughts about that, because I have been thinking about that since, Huawei, Google, IBM are doing those things. And as you said, a lot of those are companies are hiring students who have or hiring employees without domain knowledge are doing this. So I'm wondering how we should, change our curriculum and everything to kind of like meet the demand of the market, or if that's, but you probably get my question. So I just want to get your thoughts a little bit on that.
I do get your question, and of course, as you know, I don't have the answer, which I wish I did. I think having and encouraging programs that are more fundamentally interdisciplinary is a great step towards that, and encouraging building that literacy. But there just aren't very many people that bridge that gap yet. And in that sense, the problem, so to speak, I would actually go as far as calling it a problem right now, is that you don't necessarily have that ability to give the students the appropriate education. So here at UC Davis, for example, the computer science department just is incredibly oversubscribed. So even if I want to have a student in the atmospheric sciences take machine learning classes, the problem is that that student might not be able to get into any of these classes, because we're not the only field that has these issues. And B, those classes might be completely irrelevant for that student because they're just not actually addressing the problems that that student is interested in. And that's also a complaint that I hear a lot. So in that sense, what I'm personally doing in my group is trying to hire different people with different skill sets and have them actually talk to each other. But creating that space, of course, is something that I think we can learn a lot from diversity efforts, where, of course, you can have people from different cultures and different sexual orientations talk to each other, but you can also create that kind of safe space for people from different disciplines to talk to each other, because you have to be able to admit that you don't know a lot about one field and you want to learn. And creating that environment, I think, is something that, as a lab, for example, in some of the national labs, you could be embracing more, or in groups, or maybe even in departments. So with that, I want to say I recognize that problem, and I don't have an answer right now that would be generally applicable, but it really is worth noting. And I think if one were to do something and make a recommendation, it would be to not just use these methods blindly. And I know that there are a lot of efforts for review papers, for example. I've written a number with some cautionary notes, and making sure that students actually don't just dive in head first and dive in blindly, because that could both be detrimental for their graduation rates, and also for the way that we're using these methods in our field. Does that help?
Yeah, very much. Thanks for the thoughts.
Yeah, so you sort of mentioned a model where subject matter experts would collaborate with like computer science groups, and that would be a really good way to make progress. Like, just in a briefest of sense, like, what does that model look like?
That is not a question that I can answer briefly. I think it really would depend on the problem at hand. So, for example, with one of the examples with the Stommel model that I showed, I chose the Stommel model because it's a very simple analytical model. You don't really need a huge amount of background, but it's already a very powerful tool in terms of understanding, okay, can a model actually do these, sharp cutoffs, which are really important to me. And in that sense, you can take a computer scientist and say, hey, these are the things that I'm really interested in. This is a model that's really easy to implement. Let's talk about it. But if you're doing something like predicting the weather, then that is just, we've been working on these things for decades, and encoding this type of knowledge in like a bite size is just, really, really hard. The short answer to your question is, I don't know. If you figure it out, please tell me.
Okay. Well, let's go ahead and thank our speaker again for coming today. So thank you again.